Okay, this chapter talks about propagation of errors. So what are we talking about here? Look at this example. When you add two numbers, which are denoted by the variables x and y, and each number has an error, then x plus y will also have an error. And it turns out that the error in x plus y is the sum of the errors of x and y. If you look at this interval here from 4.81 to 4.99, that's interval of length 0.18. That's twice of 0.09, and notice that the error here is 0.05, 0.04. The sum of those is 0.09. This interval here is a plus or minus 0.09 interval, which has width 0.18. Now, why is it important to do this? Well, whenever you make a measurement of a number, the number always has an error. If you measure with a meter stick or measure with a thermometer, your value will have an error attached to it. And when you use these numbers in a formula, then your formula result will also have an error that depends on the errors of the original terms in the formula. And this is not just useful in measurements, but also in computer calculations, because as we've seen, when you store a number in a computer, that number also has an error. So it's very important to know how errors are affected by arithmetic. Okay. Here is a useful general formula right here, that the error in a function of several variables, x1 through xn, is given by this formula. Let's look at a particular example to see how this works. All right, so here's a practical engineering example where the quantity epsilon is a function of f, h squared, and e. And notice that this term, I could call this term a multiplicative term because all the factors within this term are either multiplied or divided. I could write that, for instance, as term as f times h inverse times h inverse times e inverse. Okay. So I call this a multiplicative term. All the factors multiply together. Now, of course, you have the inverse also, and we'll see how that affects the result. Okay. Let's use the error formula to figure out what the error in epsilon is as a function of the errors in f, h, and e. All right, so we'll work that out below. Here's the formula that you saw above. The error in e depends on the errors of h, f, and g, e. All right. When you do this partial derivative, what does this partial derivative mean? It means you take the derivative of epsilon with respect to f, assuming that h and e are constants. Now, if you go back up here to the original term, you'll see that that partial derivative is simply epsilon divided by f. So I'm going to write it that way. This is equal to epsilon divided by f. Okay. Similarly, it turns out when you take dE dH, that turns out to be equal to 2 epsilon divided by f. Divided by h. Okay. And this term we're going to get epsilon divided by e. All right. Now, if we look at the formulas, I'm going to plug in these expressions for my partial derivative. Okay, this here 1 over h squared e was the first partial derivative. This 2f over h cubed e was the second partial derivative, and so on. So let me write that this way. That's equal to e over f times delta f. Okay, and there's an absolute value there. And then the second term was e over 2 times e over h times delta h. There's absolute value there. And then the third term was e over epsilon over e, times delta e. Okay, I'm being a little bit sloppy with the absolute values, but you'll see where I'm going in a minute. All right, now notice there's an absolute value of epsilon that's common to each of these terms. So I'm going to take this entire equation and divide it by absolute value of epsilon, and I'll put the result over here. What you get is that delta. This is actually a mistake. This should be delta epsilon. Sorry. That should be delta epsilon. So you're going to get delta epsilon divided by epsilon is equal to delta f over f plus 2 times delta h over h plus delta e over e. All right. Now, what does this mean? This here is the error in epsilon divided by epsilon. I can call that the relative. That's the relative error in epsilon. Sorry, it's not working too well. E, I think my, okay, well, this is the relative error. This is the relative error in F, this is the relative error in H, this is the relative error in E. What you're seeing is that the relative error in the result is the sum of the relative errors of the individual factors. And that's always going to be true in multiplicative terms. Now, what's this 2 doing here? Well, if you remember, when I go up here, you'll see that there were actually 2 factors of H inverse here. So the relative error of this result is equal to the relative error in this F plus the relative error of this factor plus the relative error of this factor plus the relative error of this factor. So it's a very useful result to find errors of terms where the variables are multiplied together. Okay. All right, one more example shows that when you take the difference of 2 variables, you can end up with very large relative errors. And if you look at this example, you will see that this x and y are very close together. X and y themselves have very small relative errors. This error is less than 0.1%. This error is also less than 0.1%. But when you take x minus y and compute the error in that result, it turns out you get a very large relative error, 66%. Remember, you get a percent by multiplying by 100. The reason is when you subtract x minus y, the 2's cancel, and your result is very small. So the error is large compared to the result. Okay? So we're going to do an Excel spreadsheet that shows how these errors work. I'm going to do one with multiplicative factors and one with subtraction of 2 factors, and we'll see practically how this works.